Hi guys, my name is Luka Jacobowitz. I came all the way from Germany, and I'm really honored to be here. It's my first time in Israel. Yeah, so thanks a lot for inviting me. And yeah, thank you. Thank you so much. So my talk is going to be about principled error handling. And before I start, just a very quick about me. I work at Codecentric, which is a consultancy firm in Germany, but also in Bosnia and Serbia and the Netherlands. And I don't actually do consultancy work, which is cool, but yeah. I live in Düsseldorf. That's why I also co-organize the Scala Düsseldorf and Idris Düsseldorf meetups. And for those, if any of you are ever in Düsseldorf and want to give a talk about Scala, please contact me, because we're always looking for speakers, and it's always cool to have someone from somewhere else. So I also maintain a bunch of type-level libraries, cats effect, cats MTL, and Outwatch, which is like a front-end library. That's not used very much, but it's still pretty cool, I think. And I'm super enthusiastic about functional programming. I want to teach it to as many people as possible. And that's exactly why I'm here. So let's begin. So a quick overview, what I'm going to talk about today though. So first, I want to talk about how do we do error handling in functional programming. I think we saw a couple of examples today already. And of course, we have to basically differentiate between error handling in the context of side effects and without side effects. So that's the first thing. Then we're going to talk about this abstraction, usually called MonadError. And then we're going to talk about things that go beyond MonadError. And lastly, we'll just give you a few conclusions and yeah, work from there. So let's begin. So I prepared this very simple example of how to do error handling in languages like Scala, functional programming languages. And this is, of course, completely effect-free, so there's no effects going on here. This is all pure code, but it uses error handling in a way that uses either. And I think a lot of you have heard of or probably used either. Can you raise your hand if you've used either? I know exactly what okay, so you guys already all know what this does. So we have these two functions, parse user, and they either parse it correctly and return a user or return an error. And we can find users by ID. Of course, usually this kind of thing would be an effect, but in this case it's not. And it can either then return a list of projects or an error. And then we can combine them using their monad instance and this for comprehension, which is basically just sugar for a flat map and map from the monad type class. So that's easy. What else can we do? We can use this thing called MonadError, and that is basically an abstraction for error handling that is based on the short-circuiting behavior of either. Right? So either short circuits whenever it encounters the first error, and MonadError is a type class that encodes this kind of behavior. Right? So if you have an instance of MonadError and you use one of these functions, this raise_error function, then whenever you try to flat map on something that is on a raised error, it won't be able to go through because, of course, it will short circuit there. Right? So MonadError is defined in terms of the raise_error function and the handle error with function. Sometimes these are called differently. In Haskell, these are called, I think, throw and catch. But of course, both of those words are reserved in Scala. And basically, they say that, hey, if you want to raise an error, give me a type of your error E, and then I will return an f of a. And if I want to handle an error, right? So I've gotten this f of a, then I can do this with a function that takes an error, and tries to return a valid f of a. And then that should handle this. Okay. So sometimes this is also separated into two separate type classes, right? So we could also define this in terms of just one type class that raises errors and one type class that catches or handles these errors. And in cats, we use the MonadError, but this is also a way to do it, and it might be a bit more cleaner. But yeah, so let's look at the Eithert example and try to rewrite it using this MonadError type class that we just talked about, right? So we have this parse user and find user by ID, find by user ID. We don't want to find users, we want to find projects. And let's rewrite this using this MonadError abstraction, right? So what we do is we say, hey, we have this MonadError, we have this type constructor f, right, which takes a type to become a fully formed type. And we say that it has to have an instance of MonadError for this f and our error type, right? And instead of returning an either error or user, we just return an f of user. And then we do the same thing for find by user ID. And because MonadError is also, of course, a monad, we can just reuse the for comprehension. It will stay exactly the same, except for maybe depending on type inference, right? So sometimes you'll have to add some type descriptions here or there. But usually it should be pretty much the same. Okay, so this is cool. We can also do even more polymorphic programs, right? So we have, for example, here a program that is not only polymorphic in the type constructor f, right? So, but it's also polymorphic in the error type, right? So we could call this program not just with types that support the error type we had right here, right? So we can use it for any type E. And it's not a very super cool program, but it basically, what it does is, hey, it expects a value of f of int, and then if it's there, it will get it, and if it's smaller than 0, it will raise an error, or if not, it will return the value inside of that same context, but multiplied by 2. So nothing fancy going on here, but this is just a quick example of how you can use polymorphism to write these programs with MonadError. Because now what we can do is we can call this program, called program, with a lot of different types, not just either. We can call it, of course, for example, with either, right? Where we say, hey, this program is going to return either an integer or a string as its error type. Of course, we could also use different things. But what we can do as well is to use something like I/O, where because I/O is usually able to handle errors of type throwable. That is at least the convention for most I/Os out there. There's, of course, some other things, but this is valid for the cats effect I/O, as well as Scala Z7 I/O, as well as Monix task. Right? So we could run this program not just with either, but also with I/O. And we could also do it with option, right? So option is also MonadError, but it's very strictly defined that, of course, it can't have any error type. It can only have errors of type unit, right? So it's either nothing, or a type of unit, or a valid type. So you can basically see option as being an either of unit and something else. So that's option. And we have some other instances, like, for example, either t, which is the either monad transformer. And here we have an example where we call the program with either t of list, right? So we have, which is basically isomorphic to a list of either a string or an integer. And we can call that using the same program. So abstracting over all of these, over this behavior already gives us a lot of flexibility in calling this program with a lot of different instances. And I have one last instance, and that is a state t over option. And what this basically does, because state t itself doesn't have an ability to handle and raise errors, right? So either t, of course, does that, but state t is just a monad transformer. But because it does that, it can get its instance from the underlying instance. It can get its instance from the underlying monad, right? So state t of list does not have an instance of MonadError, but state t of option does have one because option itself has one. So it basically can derive these things from the underlying monad, if that makes sense. Right? And here, of course, because option only supports unit as its error type, we also have to, of course, use unit. So far, so good. We have basically three different type of instances for this monad error type. The first one are these very simple data types that operate in the pure space of Scala. And that is something like either and option that we saw, but also something like this IOR data type, which is basically an inclusive OR. It's also called these in Haskell. And basically it can be either one or the other or both, right? So it's an inclusive OR relationship. So that's the first type of instances for monad error. The second type are these IO-like types, like I told you earlier, Katz effect IO, task, Monix task. Scala concurrent future is also one, even though it's not really IO-like in that it doesn't, it's not referentially transparent, but it still behaves very similar in terms of error handling, right? It can either return a failed result or a successful result sometime in the future, and that's very similar to Katz effect IO. Then we have these monad transformers, like state T, that I just showed you, and they get their instances from the respective underlying monads. But actually, I'm going to argue that they don't really count because they're not primitive in that sense. So we're only going to look in detail at these first two types of instances, right? So these data types and these IO-like types. Okay, cool. So let's have a closer look at this monad error type class and its interface, right? So let's look at the first function, the second function actually, handle error with. And this is called catch and Haskell. And it basically gives you the ability to say that, hey, I have this type that might contain an error. Let me handle it somehow. And to handle it, I use this function that takes an error, right? So if an error occurs, and it allows us to return a new computation of f of a. But something that I thought is a bit weird, because this is like the most primitive operation of monad error. All of the other handle functions are derived from this one. And that means that, in essence, that, hey, if all the errors are handled inside of this function, so that why does it return the exact same type? That always seemed a bit odd to me. And what happens if I return errors in the return type of the f function, right? So if I have errors there, do they propagate? It's not exactly clear. So I'm a bit wary. And I think the issues I have with this are even more pronounced in another function, and that's called attempt, which is called, I think, try in Haskell. Again, try is a keyword in Scala, so we can't call it that. And yeah, so what it does is it takes a value of f of a that might contain an error, we don't know, and it will return a value of f either e or a. And that means that, hey, if it is an error, it will just return itself, but wrapped in a left, or if it's not an error, it will return itself wrapped in a right, right? I think that makes sense. But what looks even weirder to me is that now we have this f of a and this f of either e or an a, and there's no way the outer f still has any errors. So why does it have the same type? Like, shouldn't we as functional programmers try to give as many invariants into the type system as possible? And right here, we're not doing this. And that can be easily shown by just calling attempt a bunch of times on a function, on a value. And then what we get is an either of either of either of either of either. So we get this huge stack of eithers because we can keep calling attempt on it. It becomes completely nonsensical. Right? And shouldn't we represent the fact that that we handle all of the errors? Shouldn't we represent that somehow in the type system? Maybe we should. So let's try something better. And the first idea I came up with was to use two different type constructors. So we could have one that represents what we have right now, types that can fail, right? So the f of a can usually fail if it's a monad error. But we could also have another type that it doesn't have a MonadError instance, but just a monad instance. And it is completely non-fallible. That means that it can never actually have any errors. So we could try to come up with a type class that looks something like this. And it's called ErrorControl, which is an arbitrary name, but I think it's pretty fitting because it allows us to have finer-grained control over errors. And it extends monad raise, which it could also extend MonadError, but basically means that the f has to have an instance of MonadError, and the g has to have an instance of monad, which we unfortunately can't express in Scala because we can't extend monad raise of f and e and monad and in g, because that is for some reason illegal inheritance. So what we have to do is something like this. We have to use composition. So we have got to say, hey, we also need a monad instance for g. But let's look at this control error function. This control error function takes an f of a and a function of e to g of a, and then returns a g of a. And this sounds a bit abstract, so let's try and make it more approachable. So f represents all the fallible types, right? That means that f is, produces a computation that might result in an error or not. And g is a type that can never ever have any errors. So if we have an f of a, it might include any errors of type e, and then we use this function f to go from e to g of a, and that means in essence that because g of a is infallible, and we handled all of the errors with this f function, that we can now safely return a g of a, which is guaranteed to have no errors at all. So that is the most primitive function of this error control. And so what we can do with this is derive a bunch of functions to make it a bit more easier. So the first function is called intercept, and it allows us to intercept errors. So we have an f of a that might have any errors, and the simplest thing we can do is turn all of these errors into values in a, and so we give it a function that takes a value of e, a value of, an error value of e, and returns a successful value of a, and then we can get a g of a of that. And we can easily derive that by using the pure function. And can also have a counterpart of the attempt function we saw earlier, which is now sane and doesn't allow us to chain it infinitely, right? So we have an f of a that might have an error, and then we can lift that error into either, and then return it inside of this g context that is guaranteed to have no errors because all of the errors are present in this either. And we can also have something like control that is basically like intercept combined with flat map, like trial combined with flat map. So basically what we do is say, hey, this might be either an E or an A, and then you can use that however you will and to return a G of B, and then the whole computation will return a G of B because of that. And of course what we can also do is define a convenience function called trial T that will is the same as trial but will return in the monad transformer either T instead, since that's sometimes exactly what you want. Okay, so that's cool, but now we have to look at some laws, right? So we just described this behavior, but we also want to constrain it so that we also only have instances that also make sense. So the first law is kind of a parametric law, and it says that, hey, if I lift a pure value into this fallible type, f, and then I use control error, which handles all the errors, to get back a value of g, then it should be the same as just lifting a pure value into g itself. And that is, of course, that, hey, every pure value, of course, is not going to have any errors, right? So, of course, these have to be the same. If they weren't, it would be a bit weird. Another thing that also makes sense is that if we raise an error and then use the control error function with an f that takes an e to a g of a, it should be the same as just calling that function directly, right? And another law I came up with was this law that says that, hey, because raise error is guaranteed to to basically short circuit that says that, hey, if we raise an error and then flat map over it, it should not modify that value at all and just be the same as just the simple raised error value. Okay, so those are some laws. We can come up with more derived functions. So if we look back at the functions here, we can see that almost all of them, they go from like an f of a or an f of something to a g of something, right? So we're handling all of the errors. But sometimes we also want to go in the other way. So it would be really cool if we could lift infallible values of g back into f. And to do that, we can define something that's very simple. It says, it's called except, and it says that, hey, if we have these values of g that we know can't fail, we can lift them back into f basically at our own risk. And with this function, we actually gain like the complete power of monad error back, because now we have a way to get back to the fallible types. And yeah. So we could define it like this, but we could also define it in terms of a natural transformation. It doesn't really matter. Well, what it allows us to do is to have now these kind of functions, right, that go from a g of something to an a of something. And this absolve function is just the inverse of the trial function, right, of the attempt function. Is instead of going from an f of a to a g of either e of a, we can also, of course, go back the other way. And something else that's really cool is this assure function. It says, hey, I have this value that can't fail, but maybe I want to assure that some specific property is correct. So I say that, hey, give me a function that takes an a, and it might return an error, right? So and if it returns an error, of course, that f of a at the end will have that error as well. If that option returns none, then it will be a successful value in that f of a at the end. And that is something that comes up fairly often, and we can make good use of it. So now that we have this except function, we can look at more laws. And one law that comes up easily is because now we have a way to go from f to g and from g to f. And that means that we can define something called a homomorphism. And what that means is basically just it has to follow these principles, has to abide by these laws. So this is the right chart that we saw in Itamar's talk just now, and it basically is like applicative map to, but just ignore the first result type, right? So, and basically what we say that, hey, if we accept x and then y, it should be the same as accepting first x and then using the right chart on the accept y. And the same goes for pure as well, right? If we accept a pure value of g into f, that should be the same as just lifting that pure value directly into f. And of course, the same goes for flat map. So if we flat map g of a ga, with some function f, with any function f, and accept that back into f, into the f type constructor, that should be the same. That should be the same as accepting this ga and flat mapping it using the f function and then accepting that result, right? That should be the same. That's homomorphism. And we can come up with even more laws, right? So some of the laws for the derived functions, for example. And one is that if we accept a function, if we accept a value of ga, of any g of a, because g of a can never have any errors, that control error function should never actually do anything, right? So we should always return a ga back at the end. So these should be completely equivalent because ga can never have any errors, right? And so if we were to find some unlawful instance, according to this law, where the g-type constructor can have errors, this law, of course, would fail because these would no longer be the same. We can also define something like this. It says that, hey, this handle error function is from MonadError, and it's basically like the intercept function, but it returns an f instead, right? And that, of course, has to be then the same as accepting intercept. And of course, we can also say that, hey, trial and accept is equivalent to calling attempt, because that is exactly what it is, right? Trial returns a G of either of E and A, and then lifting that using except back into F, we get the attempt that comes from monad error that we saw earlier. Okay, so now let's look at the instances we can define for this error control type class. And the first, of course, is either. That's very simple. And well, our fallible type is either, where with some type E. And if we control all the errors of an either, what we get back is just a value of A, which is represented here using the ID type constructor. And of course, ID has a monad, so that's easy. And then, because ID is just the value, we can say that, hey, either A, and then a function from E to ID of A, which is just E to A. And then we return an ID of A, which is, again, just A. And, well, that is pretty easy. That's just a pattern match. And we just call the function if we have a left value. Otherwise, we just return the right value. And accepting a function, accepting a value of G of A, which is, again, ID of A, which is, again, A, into an either E of A is just using the right constructor, right? So that's fairly easy. And it's not super useful, but it gets more useful as we go. So now let's look at something for I/O. But immediately we come into the problem that what is the non-fallible version of I/O? And so there's this thing that's been around in Haskell for a very long time, and it's called unexceptional I/O, or UIO for short. And it basically is exactly this I/O type, except it doesn't have the capability to raise or handle errors. So, and it's fairly useful, but it's not very used in Haskell, I think because mostly the I/O type is so ubiquitous in Haskell, and everyone uses it, unlike in the Scala world where I/O is, like there's 5 different I/Os, and even then, not many people are using those. But yeah, so we have this UIO type. And UIO, again, is a type with absolutely no errors at all, so it can always flat map, and you're always guaranteed that your flat map chains or your bind chains are going to work. And what we can see this IO type as is basically an UIO of either throwable or A, right? Okay. So what we have right here is that IO basically is isomorphic to an unexceptional IO, right? So a thing that might have, burn 1 involve these side effects, and that will return either a throwable or a value of A, right? So that is exactly what IO is. And right now it lives in this package called cats UIO, which I created, but there are talks that it might maybe be accepted into cats effect next year or something. We don't know yet. It will take version 2.0 to get there, and we haven't even released 1.0 yet, so yeah. Okay, so let's define this error control instance for I/O. And to do that, what we do is say, hey, we have an error control that has as its fallible type I/O, as its infallible type UIO, and the error type is throwable. And of course, UIO has a monad, and then we can use this control error function to go from an IO of A and a function that takes a throwable and returns an unexceptional IO of A to an unexceptional IO of A. And of course, these are internals. We use the handle error with function on the IO directly, and that's why this whole thing ends up being safe, right? So UIO from IO is kind of an unsafe function, but because we use this handle error right here, it actually becomes fairly safe. And then accepting a UIO into IO is just calling this run UIO function, and then it just works out. Okay, that's cool. So what we now kind of realized is that if IO is just a UIO of either throwable or A, then of those 3 groups of instances I mentioned at the very beginning, only one really remains, and that is either. So everything I talked about today, all of these error controls, all of this monad error stuff, it all boils down to either's monad instance. So not even either itself, but either's monad instance. So with that said, let's look at either T. And for either T, the instance goes from an either T of G to G itself, right? because G is either T of G is just a G of either. And then if we eliminate this either thing, we just get a G back. So, of course, G has to have a monad. And then this control error function is a bit funky, right? So we have this either T of G, E, and A. So we have an either T transformer. And we have a function that goes from the error type to a G of A. And then, at the end, we want to return a G of A. And that's actually fairly simple, right? So if we call fa.value, we get back a G of either E and A. And then we can just flat map that, check if it's left or right. If it's left, apply the function to the E. We get back a G of A. Or if it's right, we get back a value of A. And then we can just lift that using pure into G, and we get back a G of A. And using the accept function is equally easy to implement. We just call the liftf function, which does exactly that. Lift the value of G of A into either T of G, E, and A. Right? That's simple. OK, that's cool. But we can also do this for all kinds of other monad transformers. I picked state T again. We can do the same thing for reader T, writer T, and all other T's. And that is basically what we're doing now, is we map the underlying instance, right? So state T only has an error, a monad error, if the F inside the state T has a monad error. And the same goes for error control. So if state T of F, if F has an error control instance, then state T of F will also have one. And that means that we can go from state T of some fallible type F to state T of some infallible type G. And of course, we say that state T of G and E has to have a monad instance. Now we use this control error function. We implement this control error function. And we say that, hey, I have the state T of F and E and A, and have a function that takes this error and returns an infallible version of state T, G, and E and A. And to do this, we just implement this. I'm not really going to go through this, but it just makes sense. We just call the underlying instance and basically forward the whole thing. I'm not going to get into this in detail. And then accept is just this map k function, which maps the underlying instance, right? So map k it just takes a natural transformation from F to some other type G. And of course, here we go from G to F. OK, cool. So now we can also define instances for this thing called bio. What? Bio? What? OK, so bio is kind of the bifunctor I/O, or the binary I/O, which is a lot like I/O, but it's parameterized on the error type. So instead of being fixed or throwable, it is a UIO is isomorphic to a non-exceptional I/O of either E or A. And that is what Pavel talked about today. And this is really cool. What can we do with this? We can also, of course, define an error control instance. And what we do here is we say that, hey, we can go from a bio of E, of some error type E, to a bio where the left type is nothing, right? So it can't have any instances because nothing doesn't have any values in Scala. And of course, bio of E has to have a monad instance, and we define this control error function using bio's own function, and we use this left widen because nothing is a subtype of all types in Scala. So bio of nothing of A is of course also a bio of E of A using this left widen thing from bifunctor. Okay, is that it? Some caveats. So error control works with two type constructors, and it can be a bit difficult. And something that's super important is that not all errors can be recovered from. So it might make sense to like have different types of errors in your application code. So there might be at least like 3 different types of errors, but we can probably think of even more. So we have recoverable errors, but we also might have errors that we can retry and some errors that we can't retry. And we can divide these errors into a lot of different types. And yeah, what I said, recoverable, non-recoverable, retriable, but also domain errors are fundamentally a bit different from something like a HTTP error or something like that, or a Stack Overflow error. And what we can do, and that's something that John I think, also came up with for Scala Z8 is to have this error control-like thing. I'm not sure what it's called in Scala Z, but it extends bifunctor instead and just lifts all of those two type parameters into the same type constructor. And then we can have this monad throw instance, a control error again, that just does exactly the same thing that we saw in the bio instance. And it's really cool, but it kind of requires an adapter for types like IO or task. So that means if your application is already based on IO or task, then you're kind of screwed, because you can't use this unless you want to wrap every single value into it. But it is really cool, and maybe if bio becomes the new standard, if the Scala ZIO or ZIO becomes the new standard, then we should totally revisit this and look at it and see how it works out in practice. So, and of course, there's also the IO OMG what the fuck semifunctor, septifunctor, not a. And yeah, because there's just so much design space here and so many different error types. So yeah, Roman, I thought that was pretty funny, so I included here. So, and what I want to get at is that error handling is something that is super difficult because there are really a lot of things at play, and we can there's so many things to screw up, and I don't think anyone really knows completely what they're doing when they're doing error handling. So maybe this gives an idea on how we can do things a tiny bit better in the future. So conclusions. UIO is kind of like the primitive type for side effectful computations, because IO is kind of like UIO and Eithert stacked together. And most asynchronous computations, they can throw errors, right? Because asynchronous computations are usually over some network, and that can always fail somehow. So usually what we want is not UIO, but it is something like IO with an error type. And so Eithert is the primitive we're using for error handling, and it gives us this short-circuiting behavior that is very similar to how we expect synchronous exceptions to work. And composing them together gives us something like ErrorControl or something like bio. So ErrorControl is kind of a way to abstract things like bio. Okay, so how do we run a bunch of IOs in parallel and accumulate errors along the way? So we're kind of out of luck here because we have this either short-circuiting behavior inside of our IO. So how do we do that? And what we can do is a new type called VIO, and that is basically just a UIO of validated. So it doesn't have a monad instance, but an applicative instance. And now we can basically use it just like we use the validated type and say that, hey, we're just going to, instead of short-circuiting, we're just going to accumulate errors along the way. And now we have this fetch that takes a string and either returns a non-empty set of errors or a valid user, and then we can just traverse it, and then we do what we said at the top. And I had to mention traverse because no one had yet before. Okay, and another thing is how do we support non-fatal errors where no short-circuiting occurs? And that, of course, is the IO type. So we can do this type IO, and that's just a UIO of IO ENA. And what I want to get with this is that either does not have to be the primitive for error handling. It's just the thing that is most useful, or what we perceive as most useful, because it's exactly like these synchronous exceptions. And that's why we have it baked into almost all of our error handling capabilities. But yeah, that is only by circumstance. I don't think there's some fundamental thing that makes either better than all the other things. It's just how we usually want to code things. So yeah, that's it for me. Thank you for listening. You can find me on Twitter at Luka Jacobowitz or on GitHub. I'm always also on Gitter. Thank you for the half applause. Yeah.